Okay, let's unpack this. When you look up at the night sky, you see stars, galaxies, this beautiful, expansive universe we live in.
Mm.
But underneath all that visible light, there is this fundamental constant, this foundational force at play. The physicist Igor Novikov, he called it the super strong gravitational field.
And that field is really the protagonist of our deep dive today, isn't it?
It is. We are looking at the ultimate consequences of gravity.
What's so fascinating here, and what our sources really dig into, is that this super strong gravity is the intellectual thread connecting two of the most mysterious phenomena out there.
Black holes.
Black holes, which warp space and time into this inescapable funnel, and then the sheer scale and structure of the universe itself. They're both fundamentally puzzles of gravity.
And you can't really get your head around either of them without Albert Einstein's general relativity.
You really can't.
Exactly. So our mission today is to get a handle on how these concepts, black holes, the cosmos, how they evolved. We're going from these purely theoretical predictions from way back in the 18th century.
All the way to the incredible observational facts we're confirming today with instruments like the Keck telescopes and LIGO.
The journey we're taking, it forces us to reconcile these two extremes, right?
It does. You have the incredibly high gravitational fields governing the collapse of a single star.
And then you have the large-scale structure and, the expansion of the entire universe. It's physics at its most extreme.
It really shows how the death of just one massive object can, in a way, mirror the very beginning of reality itself.
So we're aiming to pull out these surprising nuggets of knowledge that show how black holes aren't just, cosmic vacuum cleaners.
No, not at all. They are key organizers. They're shapers in the vast structure of reality.
So to really appreciate what Einstein did, we actually have to start before him.
Way before.
The idea of an invisible star isn't a 20th century concept. It goes back almost 250 years.
Right. To John Michel in 1783, and then later the French mathematician Pierre-Simon Laplace.
And they were working exclusively with Newton's framework of gravitation.
Completely. I mean, they were describing gravity as this instantaneous force acting between two masses. It's incomplete for what we're talking about, but their insight was just brilliant.
And it all hinged on one concept, escape velocity.
Exactly. They just ran this thought experiment. They asked, what if gravity was so powerful that the speed you needed to escape its pull was actually greater than the speed of light?
And escape velocity is something we can kind of get our heads around. To launch a rocket from Earth, to break free, you need to hit 11 kilometers per second.
Right. And if you're trying to launch from the surface of our sun, that jumps way up.
To what, 620 kilometers per second?
620. So Michel and Laplace just took that idea to its logical extreme. They figured if you could compress a star's mass enough, its escape velocity would eventually have to pass the cosmic speed limit.
300,000 kilometers per second.
The absolute limit. Their math showed that if you took a star the size of the sun and compressed its diameter down about 250,000 times
into this tiny, super dense ball,
then light itself couldn't get away. It would be an invisible star, a dark body.
So on one hand, it's an almost prophetic prediction of a black hole. But why was Newton's math not enough? Why couldn't it describe the real physics here?
That's the critical jump. Newton's theory just isn't sufficient because it treats gravity as a force. And mathematically, that force can just grow without any limit.
It can go to infinity.
Right. And Einstein's general relativity in 1915 just changed the game entirely. It reframed gravity not as a force, but as the curvature of space-time itself.
And what's the practical difference when you're in one of these super strong fields?
Well, for things like planets, the predictions from Newton and Einstein are almost identical. The difference is, what, less than 1 part in a billion? It's negligible.
But as you compress the object?
That's when it changes. Newton's equation says the gravity on the surface just keeps going up and up, heading towards infinity as the radius goes to 0, which is, well, it's a physically problematic idea.
It's an unphysical outcome. The matter can't actually hold its shape against an infinite force.
Exactly. And Einstein's theory, GR, it gives you the framework that accounts for the speed of light and the fabric of space-time. So instead of an infinite force, it predicts a moment of catastrophic collapse.
A process called relativistic collapse.
Yes. And it happens once that gravitational field gets strong enough to just overwhelm everything. All the internal pressure, gone.
And that catastrophic collapse is triggered when the object shrinks down to its gravitational radius.
More famously known as the Schwarzschild radius.
Right.
Yes, named for Karl Schwarzschild, who found the first exact solution to Einstein's field equations right after they were published. The Schwarzschild radius is the size anybody has to be compressed to for gravity to just take over and become self-sustaining.
Once you cross that threshold, there's no going back.
None. Gravity is in complete control.
And the numbers that define this threshold, they're almost funny. They're so small, it just makes you realize how incredibly dense this stuff must be.
Well, think about the Earth. Our planet's average radius is about 6,400 kilometers.
Okay.
If you were to compress all of Earth's mass into a black hole, its gravitational radius would be about 1 centimeter.
The size of a marble.
The size of a marble. Now take the Sun. Its radius is 700,000 kilometers. Its gravitational radius is only 3 kilometers.
So you have to squeeze a star that massive into a ball smaller than a city.
That's the threshold. And if that core keeps collapsing past the Schwarzschild radius, the inevitable result is the singularity.
The singularity, that might be the most difficult concept in this whole field to really wrap your head around.
I think it is. It's the ultimate state of matter in a black hole. It's a point of zero volume and infinitely high density, infinitely high curvature. All the matter that used to be a star is crushed into this single infinitesimal point.
And this is the key, right? This is where our known laws of physics just stop.
They cease to reign. That's a perfect way to put it. Our understanding of general relativity just breaks down at the singularity. We need a new theory, a theory of quantum gravity, to describe what's happening at that point.
And it's not just in black holes. Cosmologists think the Big Bang started from a singularity too.
That's the incredible connection. Studying a black hole in our universe today is, in a really profound way, like having a little laboratory for modeling the deep, deep past of the entire cosmos.
So the black hole itself is the singularity, that point of infinite density. But when we see pictures, we see that dark spherical shadow. That boundary is the event horizon.
Right, and the event horizon is a region of space. It's the mathematical boundary where the escape velocity is exactly the speed of light.
The point of no return.
It is. But
Yeah.
crucially, it's not a physical surface. You wouldn't hit a wall. You wouldn't feel anything specific as you crossed it.
But once you do,
Once you do, no light, no signal, no matter can ever communicate anything back to the outside universe. You're cut off.
I think the best analogy for visualizing this is thinking of space-time itself as a river flowing toward a waterfall.
That analogy is perfect. It really captures the frame of reference. Gravity is so strong that the fabric of space-time itself is literally being dragged inward. It's flowing.
So you're in your canoe paddling upstream.
Right, you can fire your rocket engines, paddle as hard as you can, but once you cross that critical point where the inward flow of space-time is moving faster than your maximum possible speed,
The speed of light.
you are just carried toward the center, irretrievably. It doesn't matter how much effort you put in.
And that journey toward the singularity, that's where we get to the real horror show.
Ah, yes. Tidal forces.
Which gives us the amazing term spaghettification.
It's a great term. Tidal forces describe the difference in the gravitational pull across a body. Gravity is an inverse square law, so the force is incredibly dependent on distance.
So if you're falling in feet first, the pull on your feet is way stronger than the pull on your head.
Way, way stronger, trillions of times stronger maybe. That huge differential force would literally stretch your body lengthwise,
Yeah.
axially, and at the same time squeeze you laterally.
So it pulls you apart.
It transforms your body, your atoms, your molecules, into a thin, elongated strip of superheated vapor. It is a spectacular, if terrifying, display of a non-uniform gravitational field.
And this all happens before you even get to the singularity.
Long before. But there's a fascinating exception to this, and it depends on the size of the black hole.
Right. If you're falling to a really, really big one, the experience is surprisingly gentle at first.
Precisely. If we're talking about a supermassive black hole in SMBH, the radius of the event horizon is vast.
Yeah.
Millions or billions of kilometers.
So the gravitational gradient, the slope, is much more spread out.
It is. The tidal forces right at the event horizon itself are actually pretty mild. An observer falling into an SMBH would cross that boundary feeling absolutely normal.
They might have a moment of consciousness inside the black hole.
A brief one, yes. Before the singularity's truly destructive forces finally take over much, much later in the fall.
So the key to surviving the event horizon crossing, even for a moment, is to pick the monster, not the little stellar mass one.
I wouldn't recommend either, but yes.
Now moving on from the simple, non-rotating black holes, the Schwarzschild black holes, we get to the really complex stuff, rotating black holes.
Occur black holes mathematically. When the massive star that collapsed was spinning, all of that angular momentum is conserved.
And that spin creates this profound deformation in spacetime.
It creates what's called a gravitational vortex, where space-time itself is dragged around with a black hole. The singularity is no longer a point, it's a ring. And the black hole itself isn't perfectly spherical.
And this rotation creates a whole new boundary outside the event horizon called the ergosphere.
Yes, the ergosphere is a space where space-time is just compelled to rotate along with the black hole. It's a phenomenon called frame dragging.
And inside that region, you literally cannot stand still.
You cannot. No matter how hard you fire your engines, you can't remain motionless relative to the distant stars. You are forced to move in the direction of the black hole's rotation.
And critically, this rotating space means the black hole isn't just a cosmic drain. It's a massive energy reservoir.
And one that we could, in theory, tap into. This is the Penrose process.
This is one of the most mind-bending ideas from the source material.
It really is. Roger Penrose proposed that you could extract this rotational energy because the ergosphere has regions where particles can momentarily have negative energy.
Relative to an observer on the outside, you mean?
Correct. So how do you steal energy from a black hole? The mechanism is brilliant. Imagine you drop a package into the ergosphere and you split it into two fragments.
Okay.
One fragment is designed to plunge inward into the event horizon. The other fragment gets ejected backward. But because of the insane rotational drag of space-time, it still escapes the ergosphere.
And because of the weird negative energy dynamics of the piece that fell in.
The piece that escapes has more mass energy than the original package did.
So it gains kinetic energy, and that energy is essentially stolen from the black hole's spin.
Exactly. The black hole loses a tiny bit of rotational energy and spins down slightly. It's a non-violent way to extract a colossal amount of energy.
But the idea that sounds even more dramatic, almost like a weapon, is the theoretical process of superradiance.
The gravitational bomb.
Lay out the physics for that one.
Superradiance, which was first proposed by Yakov Zeldovich, is what happens if a rotating black hole gets hit by waves of just the right frequency, say, electromagnetic waves.
Okay.
The interaction with the spinning gravity field causes the black hole to transfer some of its rotational energy into the incoming wave. It amplifies it.
Like how a photon can stimulate a cascade of light in a laser.
It's a very similar concept, and the amplification factor depends on the type of wave.
Right. For electromagnetic waves, it's pretty modest.
About 4.4%.
Yeah.
But if you're talking about gravitational waves, the ripples in space-time itself, the theoretical amplification jumps up to 138%. Now, actually building a device to harness this is completely unfeasible. But the fact that the math of general relativity allows for a black hole to act as a cosmic amplifier, it just shows the extreme physics we're dealing with.
Moving on from all that complexity, there's a simple little phrase that defines what a black hole is when it's all said and done.
Black holes have no hair.
Coined by John Wheeler. What does it mean?
It just highlights the profound loss of information during that catastrophic collapse.
Yep.
It doesn't matter if the star was made of iron or antimatter, if it was lumpy or smooth, what kind of magnetic fields it had.
All that detail is gone, shaved off.
It's erased. Once the black hole settles down, all that complex information is just gone.
And what's left? What are the only three things that define a black hole?
A black hole is completely, totally characterized by just three external measurable properties. Its mass, its electric charge, and its angular momentum or spin.
And that leads to the famous information paradox. Where does all that information go?
That's the billion-dollar question.
Now, up until the mid-1970s, the thinking was that black holes were just these eternal cosmic voids. They were perfectly black. They only ever got bigger. And then Stephen Hawking came along and just completely shocked the physics community.
He did. He suggested that black holes actually decay, and eventually they explode.
Hawking's discovery in 1974 was monumental. It showed that black holes are not perfectly black. They emit energy.
We call it Hawking radiation. And it was really the first major step toward bridging that huge conceptual gap between general relativity and quantum mechanics.
So how does a black hole, an object that's defined by its inescapable gravity, how does it manage to radiate energy outward?
It's a purely quantum mechanical effect.
Yeah.
It relies on the idea that the vacuum of space isn't truly empty. It's constantly bubbling with what we call virtual particle pairs.
A particle and its anti-particle counterpart.
Right. They pop into existence for a fraction of a second and then they annihilate each other. But right near the event horizon where space-time is so intensely curved, something else can happen.
One of the particles gets captured and the other one escapes.
Precisely. The intense gravitational field can rip the pair apart. One particle falls past the event horizon, and the other escapes out to infinity. And the energy for that escaping particle to become a real particle effectively comes from the black hole's mass.
So the black hole slowly shrinks. It radiates thermal energy,
It does, and this process is extremely dependent on the black hole's size.
which leads to one of the most counterintuitive ideas in all of this.
The smaller the black hole, the faster it radiates and the hotter it is. A tiny black hole, say one with less mass than 10 to the 15 grams smaller than an atomic nucleus, would have an enormous temperature, maybe 10 to the 16 degrees Kelvin,
And it would evaporate instantly.
and a spectacular explosion, which opens up this really fascinating possibility of primordial black holes.
Tiny ones that might have formed in the incredibly dense early moments of the universe.
And that might be evaporating today. A critical concept if you want to understand the very first seconds of time.
So we've established that black holes have to exist mathematically. But let's look at how the universe actually makes them. It all starts with the end of a star's life.
Right. The life of a really massive star is all about equilibrium. It's this constant, furious battle
The inward crush of gravity.
versus the outward pressure from nuclear fusion in its core. As long as that fusion is releasing energy, the star is stable.
But for a really massive star, much bigger than our sun, it keeps fusing heavier and heavier elements. It creates this onion-like structure in the core.
Hydrogen to helium, helium to carbon, and so on, all the way up until it makes iron.
And iron is the end of the line.
It's the ultimate tipping point. Iron fusion doesn't release energy, it absorbs it. So the moment that core is made of iron, the outward pressure just stops.
Abruptly.
In milliseconds,
Anger.
gravity takes over, leading to the relativistic collapse of the core. The outer layers then rebound off that collapsed core, and you get a massive supernova explosion.
And the fate of what's left behind, the remnant core, that determines if it becomes a black hole.
Right. The key threshold is the neutron star limit. We think it's about 2 solar masses.
So a neutron star is this object so dense that gravity has crushed everything down into a solid sphere of neutrons.
About 16 kilometers across. But if that remnant core is heavier than 2 solar masses, even the incredible pressure of degenerate neutrons can't stop gravity.
In that case, the collapse just keeps going, past the neutron star limit down to the 3-kilometer Schwarzschild radius,
And a stellar mass black hole is born.
which brought astronomers to the central challenge, right? How do you find something that is, by definition, invisible?
You can't just look through a telescope. You have to rely on indirect detection. You have to search for the gravitational footprint.
And one of the earliest, most successful methods involved looking for spectroscopic binaries. How does the motion of a visible star tell you about its invisible friend?
It all comes down to the Doppler shift. You look for a visible star that's clearly orbiting something you can't see.
You can track its wobble.
You can. By watching the periodic shifting of its spectral lines. They shift toward blue when it's coming toward us and toward red when it's moving away.
And by analyzing that wobble, you can calculate the mass of the unseen companion.
Using Kepler's laws. And if the mass of that unseen companion is, say, 10 solar masses way above the neutron star limit, it can't be a neutron star or a white dwarf.
It has to be a black hole.
That's the first line of evidence. The second, and maybe the most dramatic, is X-ray emission. This only became possible with X-ray satellites in the 1970s.
And this is where we're looking for the signature of the black hole actively feeding.
Exactly. If a black hole is orbiting a normal star, it can start siphoning off gas from its companion.
But the gas doesn't fall straight in.
No, because the system is rotating, the gas spirals inward, it forms an accretion disk, and the friction and shear in that disk are just intense. It heats the gas to millions, even tens of millions of degrees.
And that superheated gas emits powerful X-rays right before it crosses the event horizon.
It's this specific, high-energy signature that led to the first probable discovery of a black hole, Cygnus X1.
Right, identified by the Uehiro-U X-ray satellite.
They traced the X-ray source to an invisible companion, calculated its mass to be around 10 solar masses, and that was the moment black holes went from being theoretical oddities to established astronomical facts.
So from those stellar mass black holes, we now scale up, dramatically, to the true giants, the supermassive black hole.
The SMBHs. These are gargantuan. They live in the centers of almost every large galaxy, and their masses range from hundreds of thousands up to tens of billions of times the mass of our sun.
They govern the entire gravitational landscape of a galaxy.
They do, and the numbers on the largest ones we've found just And they defy comprehension.
Let's talk about the record holders. First, TON 618.
TON 618 is the engine of a hyperluminous quasar. We estimate its mass is around 40.7 billion solar masses.
40.7 billion.
And because it's feeding so intensely, it shines with a luminosity about 170 trillion times that of our sun. It is one of the brightest single objects in the entire known universe.
And then there's Phoenix A, which is thought to be the most massive one ever detected.
Phoenix A is it's colossal.
Yeah.
The mass is estimated to be approaching 100 billion solar masses.
The scale is impossible to even imagine.
It is. Our sources give this amazing comparison. If you measure its event horizon, light would take over 71 days just to circle its circumference.
71 days.
If you put it in our solar system, its event horizon would be bigger than the orbit of Neptune. It's not a stellar object anymore. It's a galactic structure in itself.
And the immense energy sources these feeding SMBHs create, that's what we call quasars.
Right, quasars, or quasi-stellar radio sources, are beacons of cosmic violence. They're the most luminous things we can see, powered by the constant immense consumption of matter by their central SMBHs.
And that consumption creates these massive luminous jets that travel close to the speed of light.
The famous Quasar 3C273 is devouring something like 600 times the mass of the Earth every single minute.
That's just unbelievable.
And those jets can stretch for hundreds of thousands of light years. The significance of quasars is that they act as these cosmological probes. Because they're so bright, we can see them from billions of light years away.
Which lets us study the early structure of the universe.
And confirms that SMBHs are just everywhere, across all cosmic time.
And we don't have to look billions of light years away to see one of these giants. Our own galaxy, the Milky Way, has its own monster.
Sagittarius A star, SGR A star.
SGRA.
It's right there in the galactic center, about 26,000 light years away, weighs about 4 million solar masses.
And though it's mostly quiet today, its gravity is why our entire solar system orbits the center of the galaxy at 800,000 kilometers per hour.
It holds everything together.
So how did scientists confirm the existence and the mass of this invisible object, especially when the center of the galaxy is hidden by all that dust?
It took a huge technological breakthrough. 2 teams, one in Europe and one in the US, led by Andrea Ghez, spent decades watching the movements of stars right near the galactic core.
And the key technology was adaptive optics.
It was. Adaptive optics is this incredible system that uses deformable mirrors and super-fast computers to cancel out the blurring from Earth's atmosphere.
So it's like having a telescope in space, but on the ground.
Exactly. It gave them perfect vision, and they could track the individual orbits of stars with unbelievable accuracy. They focused on a few stars, making these incredibly tight, fast loops around the center.
And the faster those stars moved, the more massive the thing they were orbiting had to be.
The star S2 was the perfect test case. It completes an orbit in just 16 years. By measuring its extreme speeds and the tight curve of its orbit, they confirmed the gravitational center was an object 4 million times the mass of the Sun.
All confined to a space smaller than the orbit of Mercury.
And only a black hole could fit that description.
That evidence completely changed how we see SMBHs. They weren't just destroyers anymore, they were cosmic organizers.
Actors on the galactic stage.
Exactly.
Their role is now seen as fundamental to how galaxies evolve. Their gravity helps consolidate the initial blobs of dark matter and gas in the early universe. They provide the gravitational anchors for everything else to clump together and form the galaxy we see.
But their role is two-sided. They don't just build things up, they also stop runaway star formation.
That's the other key part of their regulation. It's called feedback. When an SMBH is actively feeding, it releases those massive energy jets and shock waves.
And those outflows heat up the surrounding gas clouds.
They heat them so much that they can't cool down and collapse to form new stars. So the black hole basically sterilizes the galaxy, preventing it from using up all its fuel too quickly. It dictates the pace of evolution.
Now let's make that essential pivot to the macro scale. The physics of a black hole is general relativity, which is also the framework for understanding the universe as a whole. And the modern picture of cosmology really starts with the discovery of the universe's expansion.
That breakthrough, which we mostly attribute to Edwin Hubble in the late 1920s, was all based on measuring the velocity of distant systems.
Right. He found that distant galaxies aren't just sitting there, they're all moving away from us.
And the proof was redshift. The light from these distant galaxies had its spectral lines shifted toward the red end of the spectrum, which meant the source of the light was receding.
And Hubble put this all together into Hubble's law. The speed of recession is proportional to distance.
The further away a galaxy is, the faster it's moving away from us. And this wasn't just galaxies flying through space. It was the space between the galaxies that was expanding.
Which confirms we live in an expanding universe that started with the Big Bang.
Exactly. And that expansion theory was tied to the hot universe theory, first suggested by George Gamow in 1948.
He proposed that the initial universe was incredibly hot and dense.
And that hot universe theory made a crucial, testable prediction. The universe must be filled with a faint echo of that initial heat,
The cosmic microwave background, the CMB.
the relic radiation. As the universe expanded and cooled, that initial radiation should have redshifted down into the microwave part of the spectrum. Gamow's team even estimated its temperature would be around 5 Kelvin.
And the detection of this signal was one of the greatest accidental discoveries in science.
It really was. In 1965, Arno Penzias and Robert Wilson, these two radio astronomers at Bell Labs, they detected this persistent, uniform, unexplained noise in their antenna.
They thought it was a technical fault.
They checked everything. They even famously evicted a pair of pigeons that were nesting inside the antenna and cleaned out. Well, the pigeon droppings.
And the noise was still there.
It was still there. And they eventually realized they were detecting this faint, uniform radiation coming from every direction in the sky. They had found the CMB.
Measuring at about 3 Kelvin, it was definitive proof for the hot universe model.
And the Big Bang model didn't just get the temperature right, it also accurately predicted the initial chemical composition of the cosmos.
That's right. The conditions in the first few minutes after the Big Bang were perfect for nucleosynthesis, the creation of light elements.
And the model accurately predicted that primordial matter should be about 70% hydrogen and 30% helium by mass. And that precise abundance of helium is what we see everywhere in the universe in places where stars haven't processed the matter yet. It's strong chemical proof.
But despite all these amazing confirmations, the modern picture of the universe is really dominated by the parts we can't see.
Starting with the profound puzzle of dark matter.
Right.
Dark matter is matter that just doesn't interact with light. It doesn't emit it, absorb it, or reflect it. We only know it's there because of its gravity.
When astronomers studied how galaxies rotate, they realized the outer stars were moving way too fast.
Far too fast to be held in orbit by the visible matter alone. The gravity of the stars, gas, and dust just wasn't enough to keep the galaxy from flying apart.
So there has to be this huge, invisible halo of dark matter providing the extra gravity.
Correct. And within that hot universe model, one particle became a really important candidate for this mystery mass.
The neutrino.
The neutrino. For decades, we thought they were massless. But if they have even a tiny non-zero mass, the cosmological consequences are enormous.
And they're incredibly numerous, right?
Staggeringly so.
Uh-huh.
Far more numerous than photons or ordinary matter combined. Their sheer abundance means that if they have mass, the total mass of all the neutrinos in the universe could be 10 to 30 times greater than all the ordinary matter.
So neutrinos could actually be the main component of mass in the universe.
Absolutely. It makes them a very viable candidate for dark matter. And if they have mass, their gravitational effect would have been the most important factor in how the large-scale structures, the galaxies and clusters, first formed.
The neutrino universe idea.
It suggests these invisible particles are the cornerstone of the large-scale structure of reality.
So we've looked at the deep past and the challenging present. Let's finish up by looking at the future and some of the extreme theoretical ideas that are still out there, starting with the fate of our own home.
Yes, a rather violent picture. The inevitable collision of the Milky Way with our nearest large neighbor, the Andromeda Galaxy.
It's hurtling toward us at 400,000 kilometers per hour.
And in about 4 billion years, they will collide and merge. They'll form a new supergalaxy, maybe we'll call it Andromeda Way.
Now, direct star collisions will be rare because the space between stars is so vast.
They will, but the gravitational reorganization will be brutal. The two central supermassive black holes, our SGRA and Andromeda's billion solar mass monster, will spiral toward each other.
Consuming millions of stars and gas clouds in the process.
And for us, the risk is being thrown out completely. Due to the extreme gravitational chaos, our solar system could easily be ejected into the cold, empty intergalactic void.
A rather bleak future. Now let's move into the truly fantastic theoretical stuff. Wormholes.
Einstein-Rosen bridges. These are solutions to Einstein's equations that describe a shortcut through space-time. A theoretical tunnel connecting two distant points in the universe.
A cosmic subway.
It would be. It could let us cross millions of light years in hours or days. But the initial problem is instability.
They collapse instantly.
As soon as anything, even a single photon, tries to enter. To hold them open, you need something truly bizarre.
Yeah.
Exotic matter.
Which is what exactly?
It's a theoretical substance with negative energy density, anti-gravitational properties. It would repel gravity, acting like a strut to prop the wormhole open.
And we've never seen anything like it.
Never. Though some quantum phenomena, like the Casimir effect, hint that it might be possible.
And if you could stabilize a wormhole, that immediately opens the door to time travel.
And the grandfather paradox. If you put one mouth of the wormhole near a massive black hole where time runs slower, the two mouths would exist in different temporal flows. Traveling through could land you in the past.
But physics might have its own built-in protection.
That's the theory. Stephen Hawking's chronology protection conjecture. The moment a time loop forms, an intense wave of radiation would build up in the wormhole throat and just destroy it instantly, preventing the paradox.
So if the wormhole is the cosmic shortcut, the white hole is its theoretical opposite.
The time reversal of a black hole, an object that constantly and violently ejects matter and energy instead of absorbing it.
Is that physically plausible?
Highly theoretical, extremely unstable. They're often called the unicorns of astronomy because there is zero observational evidence for them.
But there's some speculation that the Big Bang itself could be seen as a kind of white hole.
Conceptually, yes. A massive singularity violently ejecting all the matter and energy that created our expanding universe. It's an interesting analogy.
Moving from the theoretical to the terrestrial, we should probably address the fear that sometimes pops up about creating black holes here on Earth.
The Large Hadron Collider, the LHC. This is a fear that has been thoroughly investigated and deemed completely unfounded. The experiments at the LHC collide particles at energies that mimic the first tiny fractions of a second after the Big Bang.
And in some exotic theories, those collisions could produce microscopic black holes.
In theories with extraspatial dimensions, yes, theoretically they could. But they pose absolutely no danger to Earth.
Why are they harmless?
The purpose is to study quantum gravity. But because these theoretical mini black holes would be so incredibly small, their temperature would be extremely high.
So they'd evaporate instantly.
Via Hawking radiation. Far too quickly to accumulate mass or start consuming anything. Cosmic rays with far greater energies hit our atmosphere all the time with no incident.
Finally, let's talk about the newest frontier that's allowed us to study these violent events, listening to the cosmos through gravitational waves.
Ripples in the fabric of space-time itself. A direct consequence of general relativity. They're created by the acceleration of massive objects, especially extreme events like two black holes merging.
And until 2015, they were purely theoretical. The challenge was detecting them because they're so tiny.
Incredibly weak. By the time a gravitational wave reaches Earth, the stretching and contracting of space it causes is smaller than the width of an atomic nucleus over a distance of several kilometers.
Detecting that required the creation of LIGO, the Laser Interferometer Gravitational Wave Observatory.
The engineering is just staggering. L-shaped detectors with 4-kilometer-long arms. Lasers bounce between mirrors, and when a gravitational wave passes, it minutely changes the length of the arms.
And they can measure a shift that's less than 1/10,000th the diameter of a proton.
It's mind-boggling. And on September 14, 2015, LIGO detected the signature of two black holes, 29 and 36 solar masses, spiraling into each other and merging.
GW150912.
It was the first direct confirmation of black holes in action, the first confirmation of gravitational waves, and it just opened a completely new window on the universe. It allowed us to listen to cosmic collisions that are otherwise silent.
So what does this all mean? We've gone from this conceptual idea of invisible stars through Einstein's curved spacetime, all the way to confirming these things with incredible precision. The core takeaway seems to be that black holes aren't just destroyers.
No, they're fundamental organizers. They're regulators. They dictate the evolution and the structure of the universe on the largest scales.
And this journey has completely shifted our perspective. They're not theoretical oddities anymore.
They're established facts, essential to galaxy formation, essential to fundamental physics. And yet the biggest questions are still right there at the boundary of our knowledge. What is actually inside the event horizon? What is dark matter made of? Can we ever stabilize a wormhole?
Our sources refer to the universe as an eternally evolving, eternally young universe, and they emphasize how everything, the evolution of the cosmos, the existence of life, is all intricately linked to these fundamental constants and processes.
We rely on the exact amount of helium made in the Big Bang, on the regulatory violence of SMBH's controlling star formation. It's also finely tuned.
So, given that intricate dependence, and considering all these exotic concepts we've talked about, here's our final provocative thought for you to consider.
What new, currently hidden fundamental constant, maybe one defining the nature of exotic matter or the physics of the singularity, what new constant will eventually prove to be the cornerstone of a future even more complex understanding of our reality? What unseen piece of physics is truly regulating everything we observe?